Hello, everyone. This is Professor DePaulo. Welcome you back to Psych 220 Behavioral Statistics. And today I'm going to be talking about correlation and regression. So correlation is a topic you should be pretty familiar with from Psych 100 and or the research and psych course. And we generally talk about something called Pearson's R. So Pearson's R, more technically called the Pearson product moment correlation. This is a measure of the linear relationship measure of the linear relationship between two quantitative variables or two variables measured on an interval or ratio scale. So we call these quantitative variables, we call these continuous variables, right? So these are variables measured on interval or ratio scale. And the range of Pearson R is between -1 and +1 inclusive. -1 is called a perfect negative correlation, and +1 is a perfect positive correlation. And so the direction of the correlation basically influences the interpretation, right? So a positive correlation is when both variables, so two variables vary in the same direction. That means if one variable increases, the other variable increases. If one variable decreases, the other variable decreases. Common examples, study time in terms of minutes total, studying time uh, is positively correlated with numerical grade, right? So as study time goes up, numerical grade goes up. They go in the same direction. It's a pretty strong relationship. So it's a pretty easy one to draw a conclusion about. I mean, height and weight. As height goes up, weight tends to go up. They're positively correlated, right? There's a lot of things that are positively correlated. Those are just a couple basic ones, right? Two variables vary in the same direction. They both either increase or they both decrease. Then we have a negative correlation. This is all related to Pearson R, where the two variables vary in opposite directions. So these are when two variables go in opposite directions. My favorite example here is social media use and grades as a negative correlation, right? So as social media use increases, numerical grades or final numerical averages tend to decrease because people spend so much time checking their whatever that they just can't focus on anything else. Very, very common these days. So, as I said many times before in the course, shut your phone off when you're studying. Put your social media away. Just sit, focus on what you're trying to learn, and you're going to be better for it. And the people on your social media or on your cell phone texting you every 2 seconds, they're going to be fine. Unless there's an emergency, there's no reason you can't shut it down for them, right? Another example would be pain medication and levels of pain. So the more pain medication you take, hopefully they'll lower the levels of pain that you're experiencing. So they're going in opposite directions. So those are the two most common situations we have. And then we also have the zero correlation. So let's go to the zero correlation. That means no correlation. There's just two variables vary independently of each other. So basically, there's no pattern. So the relationship becomes a zero correlation because variable X does not correspond in any way to variable Y. They don't go in the same direction, they don't go in the opposite direction. They're completely independent of each other. There's no relationship at all. So a good example of this, shoe size, so common one I always use, shoe size and IQ. So there really is no relationship. Shoe size and IQ. They don't go together at all, right? So when two variables don't go together at all, they have a zero correlation or no correlation. We graph the correlation using something called a scatter plot. This is for Pearson R, by the way. So a scatter plot is an XY plot showing the correlation. That's what a scatter plot is. And this is what it looks like. I'm no artist, but a positive correlation will look something like this. X marks the pairs of scores. So we have an X variable, we have a Y variable. The X here, or the dot, depending on what you want to draw, the X here is basically a combination of the X score, the score on one variable X, and the score on one variable Y. And then we mark a little X, or we mark a point here to delineate that person's combination of two scores, X and Y, whatever they are. Right. And as you can see here, the X's are going up from left to right. So if you were to draw a line here through the scatter plot, the slope of the line would be positive. So this is a positive correlation. Then for a negative correlation, you're going to see something like this. And you can see here that if you were to fit a line through these data points that fits these data points, the slope would be negative. So as X is increasing, Y is decreasing here. So this is a negative correlation. And then if you were to plot the zero correlation, it looked like something like this. Obviously, these are just an example. There is no relationship between X and Y here. If you were to draw a line that best fits these points, the line would be horizontal, and the slope of our horizontal line is always zero. So this is a zero correlation. So basically, imagine drawing a line that best fits these points on the scatter plot. That line technically is called the regression line that we're going to talk about. And the slope of that regression line is going to be positive, negative, or zero. And the closer the dots or the X's line up to that best fitting line, that means the closer they are to the line, the stronger the correlation, right? And positive correlation is not necessarily stronger than a negative correlation. It's the magnitude, right? So a correlation closer to one or negative one is always going to be stronger than a correlation closer to zero, regardless of whether it's positive or negative. Right? So if you take the absolute value of the correlation, that gives you the magnitude of the correlation. The strongest correlation is one or negative one, and obviously the weakest correlation is zero. So that's Pearson R, and we're going to compute Pearson R, and I'm going to talk about regression after that. Let me talk about a few other correlations. So a few other correlations here besides R and P, besides Pearson R, right? We can have something called Spearman's rho. This is a correlation between two ordinal variables. We're not going to calculate these. I'm just bringing them up that there are other kinds of correlation other than Pearson R. So if you have two ordinal variables, you can compute something called Spearman's rho. Gives you the correlation between two, so do the positions of those two variables correspond in a meaningful way. So it's two ordinal variables. Then you have something called phi. Phi is a correlation between two nominal variables. This is two nominal variables. So let's say I wanted a correlation between gender and ethnicity. Does gender correlate with ethnicity? I don't know. I mean, we can compute it. Although I wouldn't want to use ethnicity here because phi should be technically two dichotomous variables. That means that the two variable dichotomous means that there's two values for each variable. It's a binomial. It's a basically the binomial, right? Heads or tails, right? So you could look at two dichotomous variables like wins and losses could be one. Win or loss could be one variable, and gender could be another variable. You can examine if there's a relationship between gender and whether someone won or lost a particular match or a game. You would technically want two dichotomous variables, or so two 0, 1 variables here to match up. If you had more than two categories, you'd end up having something called Kramer's V, which is, I guess, I don't think it's technically a correlation. It's a relationship. I guess you can call it a correlation. If you have more than two groups, it becomes something called Kramer's V. And we're not going to be looking at that. Kramer's V, Kramer with an M here. I think I spelled it right. You could find that under chi-square, which we're not going to really look at here because there's just too much material to get through. But if you did chi-square and you were looking at nominal variables, because that's what we'd use to look at nominal variables, you look at chi-square, you could then calculate the relationship between two nominal variables that have more than two groups, and you calculate Kramer's V for that. You also have something called a point biserial correlation. The point biserial correlation is a correlation between one continuous variable, so one continuous variable and one dichotomous variable, 0, 1 variable. And one dichotomous variable. That dichotomous variable is still categorical. It's a nominal variable, but it's 0, 1. So 0, 1, only two values, right? So if you have one continuous and one discrete dichotomous variable, you calculate something called point biserial. And those are the major types of correlations. There are others, but these are the ones that I've encountered the most. Just giving you, I'm not going to walk you through all this. Point biserial is calculated the same way as Pearson R. Phi is calculated differently. Spearman rho calculated. We're not going to go through all that. We're just going to go through a basic Pearson R correlation because it's the most common. So let's look at some data and let's look at how to calculate Pearson R. Oh, not a couple other things about Pearson R. So Pearson R is the measure of linear relationship. If I square Pearson R and I get R squared, this is known as the proportion of variance accounted for. So this is a measure of effect size. So the true importance, the true magnitude of the effect of the treatment or the independent variable. Proportion of variance accounted for. Sometimes you could see it referred to as the common variance between two variables. Common variance between two variables. It's mostly used in regression, which we're going to get to. This is R squared. So if your R is 0.3, which is a fairly small to borderline moderate correlation, your R squared would be 0.3 squared, 0.09. And if you interpret this as percent, you interpret it as 9% of shared variance. So that means that one variable accounts for 9% of the variability in the second variable. Doesn't matter which variable you're looking at. They only share one of those two variables only accounts for 9% of the variance of the second variable, which means there's 91% not shared or not accounted for. And what that tells you is that those two variables are correlated, but that one variable is not doing a good job explaining the second variable. They're kind of weakly correlated, and yeah. Now, hypothesis testing for R, the null hypothesis is that there's no correlation between the two variables. And the alternative is that there is a correlation. And it's two-tailed test, right? So we don't really look at directional tests with correlations. So all you're saying is if the test of the correlation coefficient is significant, we reject the null and we conclude that there is a correlation. So another way is to write this R equals 0, null hypothesis. The correlation is 0, and the alternative R does not equal 0. So it could be either positive or negative, the two-tailed test. So you could actually use a t-test to actually test the significance of the correlation. But the significance doesn't really tell you much. It just tells you whether it's 0 or not 0. And to me, that's not that interesting. Yeah, if it's 0, it's pretty bad. That it's not really offering any information for us. If it's not 0, what could that tell us? It could still be very small and still not really provide us much going on. Like this 0.3, this might be significant with a large enough sample, but does that really tell us much between the two variables? No, because it's only explaining 9% of the variance. So 91% of the variability in one of the variables is not being explained. So it's not telling us much. It's telling us 9%, which is something, but it's not a lot. Now, in terms of the magnitude of the correlation, if R is less than 0.3, right, but it's greater than 0, it's a small correlation. These are just my sort of guidelines. So if R is greater than 0 but less than 0.3, it's a small correlation. This is also negative. So this is really absolute value. Less than positive 0.3 or closer to 0 compared to negative 0.3. If R is between, let me write this better. So if 0.3 is less than R, which is less than point 0.5 or zero point 0.6. This is a moderate correlation. Sort of my rules for correlations are pretty small in terms of moderate correlation with regard to psychology, because in psychology we have very small correlations. We have much larger correlations in physical sciences and biology. And the reason for that is because we're measuring with a lot of error. Psychology is really difficult to do research in. It's probably the most difficult field to do meaningful research in because it's so difficult to measure anything. And we always disagree about how to measure things. How do we operationalize, for example, intelligence? We can disagree on that measurement. And when there's a lot of measurement error, which is the case in psychology, our correlations tend to be smaller than, say, physics or biology or chemistry. At the same time, physics, biology, and chemistry have been around a lot longer than psychology. So maybe in the future, psychology will develop more accurate measures. And the other situation is large correlation here. So anything greater than, you can consider a large, especially in psychology, a large correlation. If this was a different field, I would make this bigger. But in psychology, if you get zero point 0.5, that's pretty damn good. I'm thrilled with zero point 0.5 in any kind of research study. Now, just think about zero point 0.5 only explains, so zero point 0.5 squared is 0.25. That only explains 25% of the variance. That means 75% of the variance is still not explained. And that's a lot of variance not explained. But I'd still be thrilled with this. If I can explain 25% of the variance, I think that's pretty good for psychology, personally. Now let's look at how we compute R to begin with. So if you look at the formula sheet, we know that Pearson R is equal to something called SP. SP refers to the sum of the cross product of X and Y. So if you have two variables and you multiply them together, X and Y, and you add them up, you get the SP value, the sum of the cross products of X and Y over the square root in the bottom of sum of squares X times sum of squares Y. If we want SP, well, I told you about the sum of the cross products. SP technically equals the sum of XY minus the sum of X times the sum of Y over N, the number of pairs of scores. So we're going to use these formulas to calculate Pearson R. So if you look at the first problem under the worksheets that we're going to do, we have driving experience and we have monthly insurance premium. I don't know if it's going to let me post here, but we're going to try. And it kind of does. Although that's kind of sloppy also. Yeah, that's kind of sloppy. So let me get rid of it. I'm just going to write it out manually because the table is a little bit hard to copy and paste it over here. So we're going to have driving experience. And then we're going to have insurance premium. How much you paying insurance per month? For those drivers out there, you realize the cost of car insurance is absolutely insane right now. And it really doesn't matter how much experience you have, but if you have more experience, you think the insurance premium is going to go down. Still going to be a lot, but it should be down less than if you're really young, especially young males. Young males have the highest insurance premiums in the country because they're more prone to getting into accidents. So these are years experience driving. So we're going to call this X, and we're going to call this insurance premium Y. And these are the values. And the values, on an exam will be easier than this. I just got a little carried away with the actual problem. I found the problem interesting. Instead of trying to make the problem simple, I took data that was interesting. And our corresponding, so each person has an X value and a Y value. So the first row is one person, the second row is the second person, the third row is the third person. So you have to line these up. So someone had 5 years, paid $64. Someone with 2 years paid $87. Now this is actually on the cheap end compared to what it is now. 12 years was down to $50. 9 years, $71. 15 years, $44. And insurance is like they're doing all kinds of statistical analyses on you if you're buying insurance. They are going to know exactly what kind of risk factor you are, how much they might have to pay if they insure you, and they're going to adjust their rates to make a healthy profit on you. So if you get into an accident, they're going to consider you obviously higher risk. You're going to cost more to them. You're going to pay a lot more. 656, 2542. And also the model of car, make a model of car you have plays a role, but we're not looking at that here. So you have an X and a Y column, and then you're going to make an X squared column, and you're going to make a Y squared column, and then you're going to make an XY column. And we're going to fill this out. So we're going to fill out our X squared. These ones are easy to square. The other column, not so much. The Y squared column, you're going to break out your calculator for this one because these are bigger numbers. So these are just squaring the Y values. And then we're going to do the XY. So we're going to take our X value and multiply by the corresponding Y value. So 5 times 64 gives me 320. 2 times 87 gives me 174. 12 times 50 gives me 600. And we're going to keep doing that. X times its corresponding Y value. And we're going to break out the calculator for this too, because I can do a lot in my head, but I can't do all of this in my head. Although I should be able to do probably most of it, but the calculator is your friend for this. Now that I have all 5 columns like this set up, I want an X column, an X squared, a Y column, a Y squared, and an XY column. Once I have all that set up, I'm going to add each column. So add each column, that's sum of X. This is sum of Y. 474. Oh no, this is not. This is sum of, I'm sorry. This is sum of y. Put the wrong value down. So let me erase that. I want sum of x squared first, which is 1396. Then I want sum of y, which is 474. Then I want sum of y squared, which is a big number, 29,642. So we got some bigger numbers here, and xy is 4739. Big numbers, but easy calculation. You just have to use your calculator one step at a time. And you're going to get smaller numbers on the exams. Don't worry. I'm not going to give you these kind of numbers. So now we're going to start plugging in. So we're going to find the sum of squares of x first. That's equal to the sum of x squared minus sum of x. We're doing the computational formula here because it's easier. We have to deal with decimals. Sum of x squared is 1396 minus the sum of x, which is 90 squared, over 1, 2, 3, 4, 5, 6, 7, 8. That simplifies to 383.5. Remember, this has to be positive or zero. You cannot get negative sum of squares. Because remember, sum of squares is the numerator for the variance, and you can't have negative variances here. So that's sum of squares x. Let's do sum of squares y. That's sum of y squared minus sum of y quantity squared over n. So we're plugging in for y now. 29,642 minus 474 squared over 8. And when we simplify the sum of squares y, we get 1557.5. That is your sum of squares y. So we did sum of squares x, we did sum of squares y. Now we're going to do the SP. We're going to calculate SP. So we have SP is the sum of xy minus the sum of x times the sum of y over n. That is your SP value. Sum of xy is this bottom, this one at the bottom here, 4739. The sum of x we have as 90. The sum of y we have as 474. And the number of pairs is 8 again. Simplifying that, 4739 minus this fraction. Simplifying the fraction, I get 5332.5. And when I subtract, I get negative 593.5. We can have a negative value here because negative value here means negative correlation. So you're allowed to have a negative value for SP. You are not allowed to have a negative value for sum of squares x and sum of squares y. This just tells us the correlation is negative because this top numerator is negative here. Plugging in for r. R is SP over the square root of the sum of squares of x times the sum of squares of y. SP is negative 593.5. Sum of squares of x, 383.5. The sum of square of y is 1557.5. And when I simplify that, I get negative 593.5 over the square root of 597,301.2. And that gives me 593.5. I'm just doing step by step. Square root of that gives me 772.85. And when I simplify that, I can round the final answer to two decimal places, negative 0.77. Now, this correlation has to be between -1 and +1. And obviously it's close to -1, but it's between -1 and +1. It's a pretty strong negative correlation here. Now, I want to plot it. I want to plot the scatter plot. So let's do the scatter plot here. So you need the X and Y values that we had before, but I have them here. So I'm going to draw the graph. This doesn't have to be a work of art. I'm not a great artist when it comes to scatter plot. So if you look at X, the range of X, the lowest value is 2 for X and the highest value is 25. So I'm going to start with 2. And then you could do it a different way, but I'm going to go in increments of 2 from 2 all the way to 26 because the highest value is 25. So 2, 4, 6. You don't have to do increments of 2. You could do bigger increments, but I figured I'll do it this way because it's just easier this way for me. You could do it a different way. You could do it by 4 if you want, if that suits you. You don't want to do it by too big of a gap because then everything's going to be kind of squished. So you like to spread out the x-axis if you can. So that's why I'm doing it by 2, although this is not a work of art here. So I want to stop at 26 because the highest value is 25. So I want to have all my values contained within this x-axis. And then the y-axis, the smallest value here is 42 and the largest value is 87. So this one's a little bit harder. I'm going to start with 40 at the bottom here, and I'm going to go up by 10. Like I said, you can go up by smaller increments, but then you're going to have a big graph. So I'm just going to go by 10. And the x-axis in general, if the x-axis is longer than the y-axis, it's fine. You just want to do your best to try to encompass. You want all the values of y here, and you want all the values of x here, that within the graph. Now I'm going to plot the first point. The first point is 5 and 64. So I find 5 for driving, which is x. Driving is x, and y is insurance. So I find 5 here, and then I go up to 64. So 5 is between 4 and 6, and 64 is between 60 and 70. And I put a dot. It doesn't have to be perfect. That's the pair, 5 comma 64. Then I do 287. So 2 here, 87 is right below the 90. That point is 2 comma 87. Then I do 12 comma 50. So 12 here, 50 here, put another dot. And I keep doing the same thing for all 8 pairs of points. 971 goes like right here. 1544 goes between 40 and 50, like that. 656, 6, and then 56 is below 60. So something like that. 25 and 42, that's way out here. 25 and 42 is just above the 40. That looks like an outlier here. And then 16 and 60 goes right here. And that's my scatter plot. And you can see there's a negative correlation because if I were to draw the best fitting line here, the best fitting line would go down. It would have a negative slope. And we're actually going to draw that best fitting line, that regression line, shortly. I'm going to start with I started with the correlation first and the scatter plot. Now we're going to move into a regression part of this. So let's say I'm not just looking at the relationship, the correlation, right? Because in correlation, we don't have causality. We only have causality in an experiment. We don't have causality ever with the correlation. We have an X and a Y value. So there's 3 ways that this can go. So X can cause Y can cause X, or Z can cause the relationship between X and Y. Right? So this relationship between X and Y can be caused by Z. Z is an external variable. It's a third variable that can influence the relationship between X and Y. So in essence, Z, which is a confound, a variable that you're not really manipulating or you're not looking at as a target variable. Something else, right? Can lead to a relationship between X and Y. For example, in the ice cream and crime correlation example, which is very famous, that there's a positive correlation between ice cream consumption and crimes committed. It's not that ice cream causes crime. It's not that crime causes ice cream. It happens to be that the temperature, the heat, causes an increase in ice cream consumption and crime because in the summer, people eat more ice cream. And in the summer, people commit more crimes because more people are out. So there's going to be more crimes committed, especially with regard to theft. And all the assault, theft. I mean, people are not hanging around outside in the dead of winter, so there's less of that crime. So in that case, the heat, the temperature causes the relationship between X and Y. So in correlation, there's no causality because you can have these three situations here that I've mapped out for you. In terms of regression, we are looking at prediction. So it's a linear prediction. We'll come back to the scatter plot in a bit. So if we're looking at linear regression, we are predicting your Y variable using X. So we're trying to use X to predict Y. This does not mean that X causes Y, but we're looking in one direction. We're looking at X leading to Y, like that. We're not looking at Y leading to X. We're looking at X predicting Y. So that's a little bit better than correlation because in correlation, it could be any of these three, right? And in regression, it's not going to be Y to X. It's always going to be X to Y. Could you have a third variable? Of course. But we're looking at X to Y. So this is a little bit more directed than correlation. It's still not causality, though. One common regression would be using high school GPA to predict college GPA, or using SAT scores after, in high school, your SAT scores to predict college GPA. Those are very common regression issues or regression analyses that the colleges run. Or using the MCAT score to predict your medical school success, or medical school GPA or graduate school GPA with some of these tests that are out there. So linear regression is you're using one variable X to predict another variable Y. So in this example, I can use driving experience, driving to predict insurance cost. So my X is driving, my Y is insurance. I'm using driving experience to predict insurance cost. That makes sense, right? It doesn't make sense to use insurance to predict driving experience because that sounds like nonsense, right? You're using driving experience to predict insurance in that one direction. So this is different than a correlation because we're only going in one direction. So to calculate the linear regression, and we're going to map out a straight line here using driving to predict insurance with a straight line. So first thing we got to do is we need to calculate the equation of the regression line, which is y hat, predicted y value, is equal to the slope times whatever whatever the x value is. In this case, it's driving, so it's years driving, is this x value, right? Plus a, the y-intercept, the point in which the line crosses the y-axis when x is 0. Right. So we need to find b and we need to find a to calculate this regression line. B is equal to the sum of the cross products over the sum of squares of x. And A is going to be equal to the mean of y minus the slope times the mean of x. So we're going to have to find the mean of y and mean of x, but that's pretty easy to do. Let's start with the slope. In this example, our SP from up top, our SP was equal to negative 593.5, and our sum of squares x was equal to 383.5. When I do the division here, the slope becomes negative 1.55. That's your slope. It's a negative slope. It's a negative correlation, so it makes sense that it's a negative slope for the prediction line, the regression line. The y-intercept, we got to calculate the mean of y. So that's simply 90 divided by 8. I'm sorry, the mean of y is 474 divided by 8, which gives us 59.25. That's the mean of y, minus the slope, which is negative 1.55, times the mean of x, which is 90 divided by 8, turns out to be 11.25 for mean of x. And when I simplify this, remember, minus a negative, this is going to be a negative value. Minus a negative is a plus. So you're going to end up turning this to addition. All right, so when I turn it to addition and I add it to 59.25, I get 76.69 as my y-intercept. And now I can plug that into the regression line. Y hat equals negative 1.55x plus a, bx plus a, 76.69. And that is my regression line using experience driving, which is our x value, to predict insurance rates. The predicted insurance rate is the y hat. That is the value on the line. So if we draw the regression line, that's what we're going to find this value, the predicted y value. So let's go back and draw the regression line into the scatter plot. Here's my scatter plot. And we want to draw the regression line into the scatter plot. You need 2 points to make a line. So what I'm going to do is I'm going to pick the y-intercept, which is our A point, right? That's going to be 1 point. Y-intercept is when x is 0. So when x is 0, the y-intercept is 76.69. So I find 0 and then 76 right here. I'm going to draw an x as my point. So that's the y-intercept right here. All I do is plug in 0 for x into the regression line equation, and I solve for y. So I'm going to pick the y-intercept, and I'm going to pick a value on the right side of the graph. You could pick any 2 points, but I like to pick 1 point from the left side of the graph and 1 point from the right side of the graph. All right. So I'm going to pick the y-intercept because that's easiest to calculate. And on the right side, I can pick anything over here. So I'm going to pick an arbitrary point. You could pick something different, but I think I'm going to go out and pick 20. So when x is 20, so this is the y-intercept is when x is 0, y is going to be 76.69. I just plotted that here. Let's pick 20. When x is 20, plug into the line. And when x is 20 and I plug into the line, I can just plug into that regression line. I'm going to do the calculation here. So it's going to be minus 1.55 times 20 plus 76.69. So I'm going to plug that into my calculator here. Negative 1.55 times 20 plus 76.69. And I'm going to get 45.69. I'm going to plot that 20 and then 45.69 is going to be between 40 and 50. It's going to be here on a right and X. I then just draw the line between the two X's the best you can. I didn't draw. I missed this X by a little bit, so the line should be up a little bit, but it's okay. It's not to be perfect. This is your regression line. So this is the Y hat equals 1.55X plus 76.69. That's the prediction line, right? So if I plug in X here, that gives me the predicted Y. The vertical distance between each point and the line is the error in prediction, right? So like this vertical distance, this is an error in prediction, error in prediction, error in prediction, right? These are all, you don't have to draw these in. These are all errors in prediction. And this is approximate because I didn't draw a perfect line. This is approximate, right? If I were to sum up all these errors in prediction, I would get zero. So I have to, it's similar to the deviation scores, right? When you sum up the deviation scores, you get zero. When I sum up these errors in prediction, I get zero, right? So when I sum up Y, the actual Y value minus the predicted Y values, I get zero. So I need to square them to get the squared error in prediction, right? And this is a measure of how good the regression line is, basically fitting the data. So this is so I want to square to get the sum of the squared errors in prediction here. Because this Y minus Y hat will give me zero. So this is the sum of the squared errors in prediction. Now, if I want to, if I'm asked, predict Y for someone with 10 years of driving experience. So 10 years of driving experience, I get negative 1.55, plug in 10 as my X, that's 10 years of driving experience. And when I solve that, I get 61.19. This is the value on the line. This is the value on the line when X is 10. It's the value on the line. That's the predicted value of the predicted cost of the insurance when you have 10 years of driving experience. So all you do is plug in X for this and solve it, and you're done with the regression. It's a lot of work. Well, this kind of problem is a lot of work because it's big numbers, right? If we want to extend this, we can look at a different problem, a problem that's even a little bit more ambitious, obviously. This is the relationship between age and cholesterol. So these are even bigger numbers just because I saw this data and I thought, hey, let's do this without regard to the amount of computational intensity it's going to lead to. It just looked like a good idea. And then our corresponding cholesterol levels are 3 digits. So here you're going to have a bigger calculation. Obviously, if you can do the big calculation, then the small calculation is going to be simple. So think of it as if I can do this, if I can understand the bigger calculation, then anything smaller, like you would expect on an exam, is going to be very, very easy to do. So age is going to be our X, cholesterol is going to be our Y. We're going to want an X squared column. We're going to want a Y squared column, and we're going to want an XY column. So you're going to have some big numbers here. So the first thing you're going to do is square all the X values. Square all the X values. We are squaring all the X values here. Square all the Y values. You're going to get huge numbers here. So your calculator is going to be working overtime on this one. But don't worry, if you can do this, you can do the small problems very easily. This is the problem when you try to work with real data instead of fabricating the data, making up the data basically to make it easier. When you're dealing with the real data, you get some bigger numbers. I use R to solve this instead of a calculator, but you can use a calculator. It just takes a little longer to use a calculator. R is pretty really efficient at solving problems. And now you're going to multiply each X value by its corresponding Y value, and you're going to get an XY column here. So I multiply each X value by its corresponding Y value. And then you're going to sum up all the columns here. Sum up all these columns. This is push through this because it's a bigger problem. This one is a pretty large number, 364,280. And this one's 98,307. So you set up the problem by making the 5 columns. Now we can calculate based on these sums here. So I only need to look at the sums for now. How do I calculate R? R is equal to SP over the square root of sum of squares X times sum of squares Y, which means that we need to do the sum of squares, right? So let's do sum of squares X, 28, 110 minus 512 squared over n, and n here is 10. When I simplify this, I get 1895.6. And then sum of squares y is 364, 280 minus 1896 squared over 10. And that simplifies to 4798.4. And now calculate SP. So SP formula is sum of xy minus sum of x times sum of y over the number of pairs. So sum of xy we have is 98,307 minus sum of x 512, sum of y 1896, n is 10. When I simplify that, I get 1231.8. All you do here is multiply out, divide by 10, and subtract that product, that quotient from this first value. And you're pretty much set up to do R here. So R is this on top, 1231.8. On the bottom, we have sum of squares x times sum of squares y square root. So 1895.6 times 4798.4. So 1231.8 stays on top. Correlation is going to be positive because the top is positive, the numerator is positive. This product on the bottom is 9095847. And the square root of that gives me 3015.932. And I can round to two decimal places. I get a positive 0.41 when I round to two decimal places. That's my correlation. Positive 0.41. Now you can make a big graph for the scatter plot if you want. The range for x, lowest value of x is 31. The highest value is 74. So 30 to 74 is a difference of 44. I'm probably going to do every 4 here or every 5. I'll do every 5. Starting at 30 because I want to contain the lowest. I want this to contain the lowest value and the highest value. The highest value is 74. So I'm almost there. Just one more. And then for y, the lowest value is 154 and the highest value is 235. 154, 230. So it looks like I'm going to be doing, let's see, 154 to 235. That's a difference of 46 and 35, 81. So I guess I can do every 10. So we can start at 150 over here, and I'll do every 10. 160, 170. Like this is more of an art than a science. And when you have smaller numbers, it's going to be much easier to do this. These are huge numbers, so I have to sort of take into account that. Yeah. The highest value is 235, so I don't have to go up to 250. I just have to go to 240. So let me get rid of 250. It's not needed. Let's leave it at 240 as the highest value. Right. And now I want to plot 50. The first point is 58, 189. So 58, somewhere in here, 189. It's close to 190. And then we got 69, 235, 69, almost at 70, 235 is way up here, close to 70. 43, 193, 43 is in the middle, 193 is over here. 39 and 177, 39 and 177, something right here. 63, 154, 63, and then 154. 52 and 191. Something like that. 47, 213, 47, 213. Something like that. 31, 165. This is only approximation because, it's really hard to estimate these exact points. 74, 198. 74 is here. 198 would be up here, close to 200. Something like that. 36, 181. 36 is close to here. 181 is close to here. As you can see, there is a positive line. If I drew a line that best fits these points, the line would have a positive slope. You do have this point down here, which is kind of pulling it down. This point up here is kind of pulling it up. So we got about 0.41, which is a moderate positive correlation. If I drew the line here, it'd be like that. So that's the scatter plot. Now let's look at the regression line. And then we'll come in and we'll put the regression line in there afterwards. For the regression line, we need to find B first. B is equal to the sum of the cross products over the sum of squares of X. The SP value is 1231.8. Sum of squares X is 1895.6. Solving for this, we get 0.65. So the slope is positive. And then the y-intercept, mean of y minus b times the mean of x. And here we're predicting cholesterol from age. We're using age to predict cholesterol. The mean of y is 1896 times 10, which is divided by 10, which is 189.6. This is equals minus b, which is 0.65. And the mean of x is 512 divided by 10, which is 51.2. So this is 189.6 minus this product. And when I do that, I get 156.32. And my prediction line then becomes bx plus a. So that translates to y hat predicted y equals 0.65 times x. This is equals, right? Plus 156.32. And there's my regression line. Now I can put that back into the scatter plot and draw in the regression line. 0.65x plus 156.32. So the first point I'm going to pick is 0, obviously. XY pairing, 0, and then the y-intercept obviously is 156.32. So let's plot that y-intercept. So 0x, 156.32, which would be right between 150 and 160. Put an X there. And let's pick a point on the right side of the graph. So we can pick, let's try 70. Or maybe not. Let's pick 60. So when X is 60, what is Y? We have to plug that in. So we actually have to do the math here. So it's 0.65 times 60, which gives us 39, plus 156.32, and that gives us 195.32. So all I did was plug in 60 for X. So 60 gives me for X, and Y is 195.32, so it's very close to 200, between 190 and 200. So like something like right here. Those are my 2 points, and then I just draw a line to connect them the best I can, which is always a challenge. There's my regression line. This line is y hat 0.65x plus 156.32. That is the regression line. Now, if I'm asked to predict cholesterol for someone who's 7 years old, so when X is 70, what is Y? So plug in 70 here, and you get 70.65 times 70 plus 156.32. And when I solve that, I get 201.82. So someone 201.82. So someone that's 7 years old is predicted to have cholesterol of 201.82. And that's the point on the line for 70, right? That would be this point. It's on the graph, it's not going to be exactly, but it's going to be this point. When X is 70, it's going to be on the point on the line here. And that's it. And these vertical distances here, once again, these are errors in prediction. The closer these points are to the line, the stronger the correlation, the stronger the regression model, the better the regression model. The further the points are from the line, the weaker the regression model. And that's it for correlation and regression. So hopefully that helps. If you have any questions, let me know. If not, bye for now. See you next time.